Let's learn about derivatives in this video. We can start by drawing a linear graph. Okay, so this is a linear graph with y versus x. See, we're drawing something like this. Okay, so this graph, if you want to find the rate of change of y with respect to x, we've learned it before in algebra. So what we can do is, let's take 2 points on the graph. Let's take it as P and another one Q. And then this corresponds for point P, we can take the value x coordinate as x1 and the corresponding y coordinate is y1, and for Q the x coordinate is x2 and the corresponding y coordinate is y2. So the rate of change of y with respect to x is then delta y on delta x, or just look at here. So when going from P to Q, x is changing by delta x. Delta x is x2 minus x1. And whereas the y coordinate is changing from y1 to y2, or this is delta y, which is y2 minus y1. So the average rate of change of y, the rate of change of y with respect to x, or the average rate of change between P and Q is delta y on delta x, and which is equal to y2 minus y1 on x2 minus x1. And we know this is nothing but the slope or gradient of the line. Okay, so the slope of the gradient of the line is rate of change of y with respect to x. Okay, so because this is a linear graph, even if you're finding the rate of change between two close points or exactly at P, the rate of change, you will get exactly the same value because it's have the same slope throughout. So the slope is actually giving us the steepness, the rate of change of y with respect to x, and so many y's you can call it. Now let's take a different graph. It's not linear this time. Instead, this is y versus x again, but the graph is not linear. Instead, it will be going something like this. Okay. And now you want to find the rate of change of y with respect to x. So you're still choosing 2 points on the graph, and if you want to find the rate of change, average rate of change between P and Q, you choose those 2 points. And what you can do is find the x and y coordinates corresponding to P and Q. This is x1 and this is y1 corresponding to P, and for Q, x coordinate is x2 and y coordinate is y2. And now the rate of change is exactly the same way. So you take the change in x, which is this one, delta x, x2 minus x1, and the change in y is this one, y2 minus y1. Or the rate of change, the average rate of change. This time you have to be very specific because you know the rate of change at different points is different, and if you're taking the average rate of change between different points inside this region, again it's going to be different. So the average rate of change of y with respect to x between the P and Q is given as the y2 minus y1 on x2 minus x1. Some textbooks write y1 as f of x1, so because y is a function of x and x1 is the corresponding x coordinate for y1, and y2 can be written then as f of x2. So this can then be written as f of x2 minus f of x1 divided by x2 minus x1. Okay, so this is actually the average rate of change, and if you just looking at this graph carefully, so this is actually the slope of the line which is actually going through this P and Q. Okay, so it's exactly the same as the slope of this line, f of x2 minus f of x1 on x2 minus x1. Or the average rate of change is the slope of the, it's a gradient, slope or gradient of the line which is going through P and Q. So this line which is going through P and Q is known as secant. Okay, now we're going to see how to find the derivative. So what is derivative first of all? It's instantaneous rate of change. That's another way of saying. So for example, if you want to find rate of change at this small point, at this point P. Okay, so we can start taking the average rate of change between these 2 points, and we can say, oh, this is maybe quite close to this instantaneous rate, but this line, you see, this is quite deviating from this line. Okay, so what we can next do is, so we can, okay, this is the average rate of change between the P and Q. And then to make it more accurate, what we can do is we can bring this Q closer to this one, and then the average rate of change is the gradient of this line. And even then it's not exactly matching with the instantaneous rate. So what we can do is you can pick more closer point and then find the gradient of that line. Or when we are bringing this point closer and closer, when it comes very close to that one, or what you have done is you are limiting this interval x2 minus x1, or we can call it as delta x, or some people call it as delta x, some people call it as h. So when this h or delta x tends to 0, it's not exactly 0, but we are bringing this q very close to point P, then we will get the instantaneous rate of change. But when we're bringing that very close to that, the secant line, the line which is going through P and Q, when this Q is very close to P, this will be becoming the tangent at that point. Or this derivative or the instantaneous rate of change is the gradient of this tangent line. So that's the derivative. So we start with the secant line and find the gradient, and then we're bringing this Q very close and close to the point P, and then the secant becomes tangent, and then we find the slope of this tangent or gradient of the tangent. That's the derivative. Suppose we want to find the derivative of the function y equals x squared. So how do we start doing it? First, what we can do is we can choose 2 points P and Q. Okay, and then we find the derivative of the secant line. So this P, the x value corresponding to that is x, and then this we can write it as f of x, and then for Q, the corresponding x value is h away from this x, so that's x plus h, and then this point is then f of x plus h. You can also write y1, y2, but this is a general kind of notation that we usually use in this chapter. So the derivative of the secant line is change in y, which is f of x plus h minus f of x, y2 minus y1, and corresponding x change is x plus h, x2 minus x1 minus x. And in this one, we want to find f of x. F of x is x squared when we substitute x, and then the f of x plus h is when you substitute x plus h for x. So it's x plus h the whole square. Okay, let's now substitute that in here. So the derivative is then f of x plus h, which is x plus h square, minus f of x, which is x square, divided by x plus h minus x is cancelled out, and which is h. And now we need to expand this out, and this then becomes x square plus 2hx plus h square minus x square divided by h. So let's do a little bit of calculation, elimination in here. X square get cancels out, and then this h is cancelled from here and here, and then what you end up with is 2x plus h. Okay, so this is the first step in finding the derivative. So you choose 2 points P and Q, and you find the gradient of that secant line. And after doing that, the next step is find the limit when this h is this interval. You're bringing this value q is very close to that, or you're turning this h, you're limiting h to 0. So when h tends to 0, limit h tends to 0, and this becomes, the derivative becomes to this average rate of change becomes 2x, because h is going to be 0, so this is then simply 2x. So this is a step in finding the derivative. So you find f of x plus h minus f of x divided by x plus h minus x, which is the average rate of change, and then you're limiting h tends to 0. So this is the notation we usually follow, limit h tends to 0. And then the way to write the notation for derivative is you can either write it as f dash x, or another way to write that is df on dx. Remember, this d is not cannot be cancelled. This is a part of the notation, df on dx. Okay, so this is how we find the derivative, and so derivative of any function can be found using this method. And this method, when you find the derivative using this method, we call it as differentiation by first principles. So this is known as the differentiation by first principles, and the derivative of any function can be found using this method. But the only thing is, as you can see, this is a long procedure, and we don't want to find derivative all the time when we are applying in different situations that follows using this method from scratch. Instead, what we do is we find the standard, the derivative of standard functions using the first principles, and then we use the final result. I hope now you understand how to find the derivative using the first principles. Now I strongly encourage you to do as many examples as you can before you jump into the next part of the differentiation.